What if everything we thought we knew about the semiconductor industry just changed overnight? For years, global tech leaders operated under a shared assumption that without access to American, Dutch, and Japanese tools, no country, certainly not China, could compete at the bleeding edge of chip manufacturing. The logic was simple. The crown jewels, EUV lithography, high-precision etching tools, specialized photoresists, ultra-pure process gases, were monopolized by the West. If China was denied access to these, it would remain generations behind. Cut them off, stall their progress. Game over. But that logic is cracking. Quiet murmurs had been growing louder. Hints that SMIC, China's top semiconductor foundry, was making moves. At first, it felt like the usual speculation. Minor node improvements, maybe a clever process tweak. No one expected a breakthrough. And then, the shockwave. Reports surfaced that SMIC had reached nanometer process capability, without a single piece of US or Dutch equipment. No ASML EUV systems. No applied materials. No Lam research. Zero Western gear. It wasn't supposed to be possible. Yet something was happening inside SMIC's tightly sealed Shanghai facility. Satellite imagery showed unusual activity. Whole cleanrooms gutted and rebuilt. Mysterious equipment no one could identify. Engineers spotted things they'd never seen before. Tools that didn't match any known configuration used in Western fabs. The pieces started falling into place. SMIC wasn't just copying, they were creating. Instead of chasing ASML's EUV machines, SMIC had turned to a radically different path. Multi-patterning lithography combined with AI-driven computational models. Machine learning replacing hardware. Algorithms compensating for physical limitations. Software became the tool. They were using code, intelligence, to etch matter at the atomic level. This wasn't imitation. It was reinvention. And it didn't stop with lithography. SMIC, working in collaboration with Chinese universities and research institutes, developed entirely new sets of materials. Photoresists, etchants, deposition chemistries, all indigenously sourced. Materials that were, until now, the domain of US, Japanese, and European firms. But here they were, born in Chinese labs, flowing through Chinese fabs. How did they move this fast? The answer is chilling. Talent. Quiet recruitment efforts across Asia and beyond. Engineers from TSMC, Samsung, even major US firms brought in under the radar. Not a trickle. A wave. Not just resumes, entire expertise clusters. Some call it a brain drain. Others an orchestrated exodus. Either way, SMIC wasn't just building chips, they were building the future. And behind the scenes, something else was unfolding. A mysterious internal initiative known only as Project Phoenix. Never officially confirmed, yet widely whispered about. An experimental R&D effort running parallel to mainstream operations. Rumors speak of quantum optimization techniques, links to China's space and defense sectors, even radiation-hardened chip designs. Some go further, suggesting coordination with aerospace agencies to build chips resilient not just for orbit, but for a future battlefield. But perhaps the most stunning revelation, China appears to have built its own semiconductor supply chain, completely independent. From the rare earth metals to the ultra-pure gases, from the crystal growth to the coating chemicals. All of it. In an industry where even the tiniest missing part can cripple a fab, China has constructed an entire ecosystem from scratch. Quietly, relentlessly, systematically. And then came the patents, buried deep in technical filings. A concept known as adaptive node technology. Not a fixed node like TSMC's 5nm or Samsung's 3nm. A dynamic node. A manufacturing platform that adjusts itself to the chip it's making. High-performance chips, low-power IoT devices, AI inference engines, all on the same line, without the need for costly retooling. That's not iteration. That's a complete reimagining of how semiconductors are built. This breaks the rules. And the design? SMIC engineers aren't designing chips to fit manufacturing processes. They're co-developing the chip and the process simultaneously. Design technology co-optimization, DTCO, but on steroids. AI-driven design tools that are directly linked to manufacturing parameters. Every chip blueprint is aware of how it will be built. It's a closed-loop system, an intelligent one. Feedback from one generation directly shapes the next. Smarter designs enable better fabs, and better fabs produce even smarter chips. It's a self-accelerating cycle. And early results? Though still unconfirmed publicly, leaked industry benchmarks suggest SMIC's 2nm chips are not just competitive. They may actually outperform equivalent nodes from TSMC. Lower power consumption, comparable speed, higher yield rates. If that's true, this isn't a leap. It's a coup. And now, The question no one wants to ask out loud: what if the West never had the control it thought it did? What if decades of dominance, built on the assumption of exclusivity, were never as secure as they seemed? SMIC didn't just breach a technological wall. They may have detonated the foundation of the global semiconductor order. This is no longer a story about chips. It's a story about independence. About a nation shut out from the global tech table deciding to build its own, and choosing not to invite anyone else. It's about what happens when the rules stop applying, when assumptions crumble, when a once blocked competitor starts playing by their own logic. Because if SMIC can do this without ASML, without Lam, without Tokyo Electron, then what happens when they do it better? What happens when they scale it? The cost? A fraction of what Western companies spend. The speed? Faster than anyone expected. The impact? Deeply geopolitical. For decades, the US maintained leverage by controlling access to high-end chip making. That control dictated who got to innovate, who got to compete, who got to build the future. Now that control is slipping. SMIC didn't just make a chip. They made a statement. We don't need you anymore. And if that's true, the semiconductor war just entered an entirely new phase. The entire concept of strategic technological separation, once seen as a credible mechanism for containment, now feels increasingly irrelevant. What used to be a manageable gap has become a collapse of the old order. China hasn't just narrowed the lead. It appears to have bypassed the traditional development curve altogether. This isn't a tale of catching up. It's the rise of an entirely different technological order. We're not seeing a race to equality. We're witnessing the birth of a new framework, and the tremors are already shaking global markets. Industry leaders like Applied Materials, Lam Research, even ASML, firms long considered untouchable in the semiconductor realm, are now facing the unnerving prospect that their influence might be diminishing. Internally, these corporations are urgently investigating the scope of SMIC and SMIT's progress, examining not only what has been accomplished, but how fast, how deep, and how disruptive it could be. But the disruption doesn't stop with manufacturing tools. It reverberates across the entire silicon landscape. Chip designers, IP licensors, integrators, consumer electronics brands, hyperscale providers, every participant in the value chain is being forced to rethink long-standing assumptions around price, availability, and capability. If Chinese fabrication can now deliver equivalent or superior results with a significantly lower capital burden, the financial model changes for everyone. Suddenly, what used to be safe bets are being questioned. The conversations at the top aren't just about catching up. They're about the unknowns. What else has been achieved that hasn't come to light yet? Zooming into the technical realm reveals just how groundbreaking this actually is. SMIC's 2-nanometer node isn't just a refinement of prior iterations. It's a complete reinvention. Dubbed hybrid patterning architecture, the approach fuses traditional photolithography with electron beam techniques and atomic scale deposition processes that, in much of the Western world, remain on the edge of research. This isn't a minor tweak. It's a leap into uncharted fabrication science. Central to this are next-gen materials, intelligent photoresists, and reactive etchants that don't merely react to energy exposure, but self-organize at the molecular level. This enables patterning of features smaller than the wavelength of light used, essentially overcoming the historical diffraction ceiling once thought unbreakable. We're talking about atom-level manufacturing, actual nanofabrication, where precision happens at the molecular level to unlock a fidelity of control previously seen only in theory. What's even more remarkable is how SMIC has systematized this complexity. Each facility is reportedly equipped with tailored supercomputing systems, purpose-built for computational lithography, capable of adjusting millions of parameters in real time. These AI-enhanced platforms recalibrate everything from exposure intensity to physical chip layout dynamically, ensuring optimal output, consistency, and minimal defects. And then there's the quantum barrier, a challenge that has haunted the semiconductor roadmap for decades. As transistors shrink to sizes nearing atomic dimensions, quantum effects like tunneling create instability and energy loss. SMIC's breakthrough, labeled quantum confinement engineering, turns that obstacle into an asset. Rather than resisting quantum mechanics, their transistor design channels it, containing quantum states instead of suppressing them. The result is a dramatic reduction in leakage, paired with improvements in speed, size, and power efficiency, far beyond what's currently available in mass production. What turns this from impressive to astonishing is the timing. Multiple insiders indicate that SMIC could roll out these 2-nanometer chips in volume as early as the close of 2025, possibly even preceding TSMC's launch window. And the roadmap is already extending further. Development on an advanced so-called adaptive 1.4 nanometer process is reportedly underway, targeting a 2026 release. This isn't just a case of catching up. It's a redefinition of the innovation timeline. The cadence of technological advancement itself is shifting, and with that shift comes massive systemic consequences. Brands that once had no alternative to TSMC now have viable options. Cloud providers can rethink cost-performance trade-offs. Automotive manufacturers building next-gen autonomous systems may gain easier and cheaper access to high-performance chips. This isn't just competition. It's a rewrite of the entire strategic playbook, and the ripple effects don't end with the private sector. Government defense systems, aerospace operations, and intelligence networks, all of which demand high reliability, tamper-proof semiconductors, may now find access points that don't require navigating politically sensitive or fragile global logistics. And then there's the environmental angle. Early assessments indicate that SMIC's process may consume up to 40% less energy than existing manufacturing methods. A staggering potential gain in an era where sustainability isn't optional but mandated. In a world under mounting pressure to decarbonize, this could become a defining advantage across the industry. We're living through a moment of profound inflection. The long-standing belief that technological supremacy was the permanent domain of a few dominant players is disintegrating. What once seemed like immutable truths are now up for renegotiation. The fundamentals have shifted, and the reverberations are already being felt across every major sector, from personal electronics to global defense. But it's crucial to understand, this isn't a culmination. It's an origin point. SMIC's advance doesn't signal the end of a race. It signals the beginning of an entirely new phase of innovation. The big question now isn't whether legacy players will counter, because they have no choice, but how quickly they can adapt, how aggressively they're willing to rethink their models, and whether they're structurally capable of surviving in a new reality where yesterday's rules no longer apply. So, what does this mean for you? Whether you're allocating capital, architecting next-gen platforms, or simply depending on the tech woven into daily